Welcome to Next Gen Manufacturing. This is where we get into the nitty-gritty of how stuff gets made. And today, we're diving into some materials that are, quietly running the world. Plastics and composites. They're defining the future of manufacturing as we speak. But to really get a grip on the future, we've got to look back. And it all starts with, a pretty simple problem. Picture this. It's 1869. There's a big competition to replace the ivory in billiard balls, right? The winner? A new material called celluloid. It was one of the very first synthetic polymers, and let me tell you, it lit the fuse on a revolution that totally changed, everything about how we build things. And this was so much more than just inventing a new substance. It was like handing engineers a brand new toolbox, one that let them go way, way beyond the old limits of metal and wood. And what's so wild is just how different these things were. I mean, think about it. On one side, you've got your classic materials, right? Metal, wood, they're heavy, they rust, they rot. But then boom, these new synthetic polymers show up. And they've got all these incredible advantages. They're super lightweight, they don't corrode. And this is the big one, the real game changer. You can mold them into pretty much any shape you can dream up. This meant engineers could suddenly combine a bunch of different functions into one single elegant part. Just incredible. Okay, so we get why they were such a big deal, but to really wrap our heads around them, we need to zoom way, way in, like down to the molecular level. What are these things, really? So at its heart, a polymer is just this gigantic molecule. The easiest way to think about it is like a super long necklace made of tons and tons of identical beads. Each one of those little beads has a name. It's called a monomer. And when you link them all together, you get the polymer. It sounds simple, right? But that simple idea is the key to all this incredible complexity. Want an even simpler picture? Okay, just imagine a big bowl of spaghetti. Long, tangled chains all mixed up. How those chains wrap around and tangle up with each other, that's what gives every single polymer its own unique personality. It's the difference between a flimsy plastic bag and a super tough car bumper. It's all in the tangle. But of course, not all polymers are created equal. They basically split into two big families. First up, you've got thermoplastics. Their chains are kind of linear, so when you heat them up, they can slide past each other. This means you can melt them down and reshape them again and again. Then you've got the other camp, thermosets. These guys form this super rigid 3D network of chains that are all linked together. And once they're cured or set, that's it. It's an irreversible chemical change. No going back. And here's the best way to remember the difference. Thermoplastics are like chocolate. You can melt a chocolate bar down and reshape it into something else, right? No problem. But thermosets, they're like bread. Once you've baked that loaf, it's baked. You can't turn it back into dough. It is set forever. Okay, but what happens when you need something with next-level strength? Well, that's when you call in the composites. The idea is actually pretty simple, but it is so powerful. You take your basic polymer, that's called the matrix, and you mix in these super strong reinforcing fibers. It's like a superhero team-up, creating a brand new material that's way, way stronger than either of the parts by themselves. And listen, we're not talking about like cotton threads here. These are serious high-performance reinforcements. We're talking about glass fibers, incredibly strong and ridiculously lightweight carbon fibers, and those super tough aramid fibers. You've definitely heard of the most famous one, Kevlar. All right, so we've got the ingredients for these amazing materials. Now for the big question. How do we actually turn them into the products we use every day? This part, the crafting process, this is really the heart and soul of modern manufacturing. Probably the king of all processes is injection molding. It works like this. You start with these little plastic pellets, right? You feed them into a machine where a giant screw heats them up, melts them down, and then, bam, it injects that liquid plastic into a super precise mold under tons of pressure. It cools down, gets solid, and pops out. It's an incredibly fast process, and it's how billions, literally billions, of complex plastic parts get made every single year. Another really clever method is called thermoforming. This one's a bit different. You start with a flat sheet of plastic, you heat it up till it's all soft and pliable, kind of like a warm pizza dough. Then you just use a vacuum to suck it down tight against a mold. It's a brilliant way to make things like food packaging, all those plastic trays, and even big panels for cars or appliances. So this brings us to a really critical point. Choosing the right material and the right process, it's not as easy as just picking something off a menu. For engineers, it's like solving this massive, complex puzzle. You have to balance all the properties, the performance you need, and all the tricky trade-offs that come with it. And this table right here really shows you the raw power of composites in black and white. So let's take a pretty standard polymer, polyamide. On its own, its tensile strength, which is just a fancy way of saying how much you can pull on it before it snaps, is around 60 megapascals. Okay, not bad. But now, look what happens when you add just 30% glass fiber to the mix. The strength skyrockets to 230 megapascals. That's almost 4 times stronger. And that right there is exactly why composites are so crucial for anything that has to handle a lot of stress. But like with anything that sounds too good to be true, it's not always that simple. Working with these amazing materials comes with its own very unique set of problems for engineers to solve. So, what's the catch? And here is a perfect example of one of the biggest catches: thermal expansion. This chart says it all. See how much that polymer bar grows compared to steel or aluminum? Polymers expand and shrink with temperature way more than metals do. Now imagine you bolt a plastic part onto a steel frame. If you don't design for that difference, when the temperature changes, all that pushing and pulling is going to cause some serious stress. The part could warp, or even worse, it could just snap. So where is all of this headed? What does it mean for the future? Well, as we head into this next chapter of manufacturing, the conversation is getting bigger. It's not just about performance anymore. Now we have to think about the entire life of these materials, from cradle to grave. And that's where sustainability becomes a huge driver of innovation. We're getting so much smarter about closing the loop. You've got mechanical recycling. That's basically just grinding up old thermoplastics and remelting them. That's been around for a while. But the really exciting cutting-edge stuff is happening in areas like chemical valorization. That's where scientists are literally using chemistry to unzip those long polymer chains all the way back into their original building blocks, the monomers. This means we can create brand new, top-quality materials from garbage. It's a total game changer. You know, when you look back at human history, we define entire eras by their materials, right? The Stone Age, the Bronze Age, the Iron Age. Well, there's no doubt that for the past 100 years or so, we've been living deep in the Polymer Age. And when you think about how incredibly versatile and high-performing they are, and now how we're making them more sustainable, it just leaves you with this one massive, exciting question. What are we going to build next?